Hello, in this video, we're going to be doing derivation practice, deriving an expression for indicated variables, practice for the AP Physics 1 or AP Physics C exam. In this video, we will focus on problem number 10. Please remember to pause or rewind the video as needed. Let's begin. Read along with me, please. A solid cylinder of mass m, radius r, and rotational inertia 1/2 mr squared, and a centered hole of negligible radius is placed above a rod securely attached to a smooth table so that it spins without friction. A launcher of negligible mass is fixed at a radius little r on the cylinder. Starting at rest, a launcher shoots a projectile with mass m at speed v, causing the cylinder to spin. So basically what's going to happen is an explosion, really, separation, like the recoil of a bullet in a gun. The projectile is going to fly this way and the cylinder will rotate that way, the opposite way. They will have equal and opposite momenta. Derive an expression for the speed of the launcher after it shoots the projectile in terms of big M, big R, m, little r, and v and fundamental constants. This question is about conservation of angular momentum, simply because the object is going to essentially be changing its rate of rotation. First, it's not moving at all, and then it all of a sudden starts moving, and yet no net torque is acting on it, right? No net torque is acting on the system because the torque produced by the projectile is the same torque that the projectile produces on the launcher. So they're equal and opposite torques. So there's no net torque on the system. And that is how we know conservation of angular momentum is conserved. The equation we get to use for that, conservation of angular momentum, is L initial equals L final, or angular momentum is the variable L. So first, let's go ahead and discuss what's going on here. L initial. Well, initially, there is none. Nothing's moving. But afterwards, what happens is a couple things. The cylinder is going to rotate with L equals, and I'm going to call this negative I omega. Okay, the reason I'm going to call it negative I omega is because it's kind of moving clockwise, opposite the direction that the projectile is going. And then the projectile is going to be moving with L equals mv little r, because it's only little r away. It's not full radius away. Okay. Now, if L initial equals L final, then basically having no momentum to start is having no momentum to end, and these two momenta should be equal and opposite to essentially add up to zero. So 0 equals 0 is what happens. So 0 is going to equal negative I omega for the cylinder plus mvr for the mass. If we add this to the other side, we get I omega equals mvr. Well, let's go ahead and make some substitutions here. We'll go ahead and substitute for I, and you're also going to substitute for omega as well. So let's go ahead and make these substitutions along the way. First, what I'm going to do is I'm going to solve. Let's see. Let's go ahead and substitute for I. So I is 1/2 m r squared times the omega right here, and then that's going to be equal to m little m, the mass of the projectile. So let's make sure we differentiate this. This is big M. So 1/2 big M, okay, r squared. And then this is m times v times little r. So let's make sure we differentiate this. If we go ahead and solve for omega, omega is going to be equal to, you have to multiply by 2, divide by big M r squared. And omega would be 2m vr, 2 little m, little v, little r, divided by mr squared. Okay, now why would we want to do this? Well, we want to derive an expression for the speed of the launcher. Well, That's where I told you you have to be ready to use your, anytime you're doing a rotational energy, or in this case, rotational momentum, we have to be able to use our linear angular relationship. So V for the launcher is equal to R omega. So we are going to substitute that right there. And V of the launcher will be R times 2 mVr over mr squared. And so V of the launcher would be 2 mVr squared over big M, big R squared. If the mass were increased but shot at the same speed, would the launcher's final speed increase, decrease, or stay the same? So what do we know about this? Take a look at the relationship here. The speed of the launcher is directly proportional to the mass. So it's talking about mass increase. It's directly proportional to the mass of the launcher. So an increase in mass would result in an increase in speed. So the launcher speed would increase. Okay, and then finally, if the radius of the launcher is increased or decreased rather to 1/4 of the radius, by what factor would it change? Well, we can see that the speed of the launcher is proportional to the square of the radius, right? Of the where the launcher is, which is little r. So the speed of the launcher would be directly proportional to essentially 1/4 squared, which would be 1/16. So what that basically means is the launcher speed would be 16 times smaller, be decreasing by a factor of 16.